In this video, we're going to continue our discussion on polynomials and extend it into rational functions. Now, a rational function is what it sounds like. It's a function that's made up of a ratio. And parts of those ratios happen to be our polynomials that we've learned so much about. So our definition, let's let P of x and Q of x be polynomials. And we're going to specify that Q of x is not 0. Then the function that's defined by P of x over Q of x is called a rational function. So a rational function is just a ratio of our polynomials. Now, something about rational functions that's different from polynomials is rational functions have lots of asymptotes. So we're going to learn all about some different types of asymptotes. I know most of you probably have already dealt with vertical asymptotes before, and that's where we're going to start. But there's also things called horizontal asymptotes and also slant asymptotes. And we're going to talk about all of those in this video. So first, let's just get some notation figured out. So here's a graph of a function. This is going to be a graph of a rational function. And the graph of the function looks like this. This particular function happens to be f of x equals 1 over x minus 2. But that's not really important right now. The important thing is we can see it has a break in it. It has what's called a vertical asymptote, which we will define more rigorously in just a little bit. Now, we're going to work with some specific notation that's going to carry over into calculus when we get there. So, our first thing is as x and an arrow and infinity. And we want to answer what happens to f of x. So what this is saying is as x gets closer and closer to infinity, f of x gets closer and closer to what value? And you can see as we get closer and closer to infinity, meaning my x is getting bigger and bigger and bigger, my graph is flattening out to my x-axis, which is y equals 0. So f of x approaches 0. And similarly, we can look in the other direction. As x approaches negative infinity, my function goes to 0. Now here's some kind of strange notation. I have as x approaches 2, but then I have a little negative sign up there. That just means I'm approaching 2 from the left side. It's approaching it from numbers that are slightly smaller than 2. So as x approaches 2 from the left side, what happens to my function? Well, here's 2. If I'm coming at it from the left side of my graph, my function's going all the way down to negative infinity. Similarly, if I have the same notation but with a little plus up there, that's approaching 2 from the right side. So the plus means from the right. Then f of x is going to approach positive infinity because the graph is going up forever. We're going to use this notation in our definition for some of our asymptotes. So here's a definition of a vertical asymptote. A vertical asymptote is a line x equals c where our function approaches either plus or minus infinity as x approaches c from the left or x approaches c from the right or both. So this is, in our last graph, that would be x equals 2 as our vertical asymptote. When we approach 2 from both left and right side, our function went either to positive infinity or negative infinity. Now it only has to approach positive or negative infinity from one side to technically be a vertical asymptote, but a lot of the time it goes on both sides, either both agreeing or in opposite directions. But a lot of times it looks like that same shooting up to infinity or down to negative infinity, regardless of which way you approach the asymptote. Now, how do we find these vertical asymptotes? Well, vertical asymptotes show up when you end up dividing by 0. So for a rational function, f of x equals p over q, if p of x and q of x have no common factors, and if c is a real 0 of the denominator, q of x, then x equals c is a vertical asymptote. Of our function. So the one thing that's a little bit tricky here is this line saying have no common factors. What this is saying is if I have an x minus 1 in the denominator and an x minus 1 in the numerator, x equals 1 may not be a vertical asymptote. If they would have all canceled out, you end up with a hole in your graph instead of an asymptote. So to find all the asymptotes, you figure out where you divide by 0 and make sure that it wouldn't have canceled out with a similar factor in the numerator. So let's do an example finding some vertical asymptotes. Let's find all the vertical asymptotes of the function h of x equals x plus 7 over 2x squared minus x minus 10. So what you need to do to find your vertical asymptotes is factor everything. Factor the numerator and factor the denominator. In this particular problem, we don't need to factor the numerator. It's already as factored as it gets, but we have to factor the denominator. So let's go ahead and factor the denominator. And just as a quick little review, remember we want to find two numbers that multiply to my a times my c, so that's negative 20, and they add up to my b, which is negative 1. The numbers that will do that for us are negative 5 and positive 4. So to factor this with the AC method, we have to split our negative x into a negative 5x and a positive 4x. And then we factor by grouping. In this first group, all they have in common is an x, so I get a 2x minus 5 left behind. And my second group has a 2 in common, leaving 2x minus 5. Which means that my denominator factors as 2x minus 5 times x plus 2. Let me fill that in up here. So now I have my rational function with the numerator and denominator fully factored. The reason you have to do that for both the numerator and denominator is, remember, our vertical asymptotes come from where we divide by 0, but it can't match a common factor in the numerator. So if I look at my factors right now, I don't have any common factors between the numerator and the denominator. So that just means that I get a vertical asymptote everywhere my denominator equals 0. So either 2x minus 5 is going to be 0, or x plus 2 is going to be 0. This first one gets me 2x equals 5, which is x is 5 halves as one of my vertical asymptotes. My other vertical asymptote is x equals -2. And notice that I'm writing these as equations for the vertical asymptotes. Just saying -2 or 5 halves is not good enough. A vertical asymptote is a vertical line, so you need to have x equals the number to make the equation of that line. All right, so we have 2 vertical asymptotes for that rational function. Let's do another example trying to find vertical asymptotes. So find the vertical asymptotes of f of x equals 2x squared plus 5x plus 3 divided by x plus 1. Now, right now, a lot of you are probably thinking that we have a vertical asymptote when x is equal to -1, because that makes that denominator equal to 0. But remember, you have to check to make sure it's not a common factor with the numerator. So we're going to have to factor the numerator to figure that out. So I need to find 2 things that multiply to 6 and add to 5, and that's going to be 2 and 3. So this factors, I have 2x squared plus 2x plus 3x plus 3, and then group it. I can pull a 2x out of the first group with x plus 1 left, and I can pull a 3 out of the other group with x plus 1 left. So I have x plus 1 times 2x plus 3 as the factored version of that numerator. So now it's fully factored, and you can see that this x plus 1 I have on both the top and the bottom. So if I were to cancel things out, they would disappear. All that that means is there is not a vertical asymptote at x equals -1. Instead, we have a hole there. Not a vertical asymptote. If we were to graph this, what this would look like is at this point, -1, 1, we would have a hole in the graph. And then it would look like a straight line everywhere else. Because if I could cancel those out, I would get the equation 2x plus 3, which is a linear equation. So the graph ends up looking exactly like 2x plus 3, except it has a hole because of what we had in the denominator. All right, so we've talked about vertical asymptotes. Now let's talk about horizontal asymptotes. Y equals D is a horizontal asymptote if f of x approaches D as x approaches positive or negative infinity. So that just means that as I plug in bigger numbers, either in the positive or negative direction, my graph ends up flattening out to a horizontal line. Now, horizontal asymptotes are kind of special. You know, vertical asymptotes, you're always told your graph cannot touch these asymptotes. And that's true. Horizontal asymptotes, it's a different story. Your graph is allowed to touch the horizontal asymptote, It's allowed to cross it. It's allowed to touch it many, many times. The important thing is that on the far ends of the graph, it ends up flattening out to that horizontal line. That's all you need for it to be a horizontal asymptote. Now, how do we find horizontal asymptotes of a rational function? Well, for our rational functions, which remember are p over q, where p and q are polynomials, if the degree of p of x is greater than the degree of q of x, so this is saying if the highest exponent in the numerator is bigger than the highest exponent in the denominator, that means that there is no horizontal asymptote. And now if the degree of the numerator is less than the degree of the denominator, then that means that y equals 0 is the horizontal asymptote. So if the degree of the denominator is bigger, then your x-axis ends up being your horizontal asymptote. And there's only one other possibility, which is if the degrees are equal. If the degree of p of x equals the degree of q of x, that means the horizontal asymptote is y equals k, where k is the ratio of the leading coefficients. Now that sounds way more complicated than it is. That just means look at the number multiplied in front of the term with the highest power, and just write them as a fraction. The number in front of the highest power in the top over the number in front of the highest power on the bottom. Let's do some examples of all of these situations to make it a little more clear. All right. So, example. Find the horizontal asymptote. Our first one, we have f of x equals 7x squared plus 2x over 4x squared minus 3. So to figure out the horizontal asymptote, you just have to look at the degrees of the numerator and denominator. The degree of the numerator is 2, degree of the denominator, also 2. They agree. So since the degrees are the same, this tells me that y equals the ratio of the coefficients is going to be the horizontal asymptote. My leading coefficient on the top is 7, leading coefficient on the bottom is 4. So all that this means is when I plug in bigger and bigger values for my x in either the positive or negative direction, my graph flattens out to the horizontal line, y equals 7/4. All right, let's do another one. How about if f of x equals 4x to the third plus 2 over 2x minus 1? What are the horizontal asymptotes? Well, this time the degree of the numerator is bigger than the degree of the denominator. That means that there are no horizontal asymptotes. It goes towards either infinity or negative infinity the further out you go. Last one. F of x equals 5 over 4x squared plus 9. The degree of my numerator is 0. Degree of denominator is 2. The denominator has a higher degree, so this means that y equals 0 is the horizontal asymptote. These are the only 3 cases with rational functions. You either get the x-axis, y equals 0, you get none, or you get the ratio of the coefficients. Now remember, I said that it's okay for your graph to touch horizontal asymptotes. So as an example, let's look at this function, g of x, which is 3x squared plus 4x minus 3, divided by x squared plus 3. And we want to find any points where g of x crosses its horizontal asymptote. Well, the first thing we should do is figure out what the horizontal asymptote is. Then we can figure out where our graph crosses it. So since I find my horizontal asymptotes by looking at the degrees, notice the degree of the numerator is 2. The degree of the denominator is also 2. So that tells me that the ratio of those leading coefficients is going to be my horizontal asymptote. My leading coefficient of the top is 3. Leading coefficient of the bottom is 1. So that's just y equals 3 is the horizontal asymptote. So now to find where my graph crosses this horizontal asymptote, that's just asking where is my function equal to 3. So to find the points where it crosses this horizontal asymptote, we just have to set the entire function equal to 3 and solve that equation. So once I solve this, I'll have all the x coordinates of where our graph crosses the horizontal asymptote. To solve this, multiply both sides by the denominator. So I get 3 times x squared plus 3 equals 3x squared plus 4x minus 3. Distribute on the left side to get 3x squared plus 9 equals 3x squared plus 4x minus 3. Now if I subtract 3x squared from this side and move it to the other side, the 3x squareds cancel out. I just get 9 equals 4x minus 3. Add 3 to both sides, and then divide by 4. So this tells me that when x is equal to 3, we cross the horizontal asymptote. But the question was asking us find the points where it crosses the horizontal asymptote. This is the x coordinate. What's the y coordinate? Well, we actually already know. Remember, our horizontal asymptote was y equals 3. So if we're crossing it there, my y coordinate of the point is also 3. So now we've talked about vertical asymptotes and horizontal asymptotes. We have one more type of asymptote to talk about, and they're the trickiest ones. They're called slant asymptotes, and that's exactly what they sound like is exactly what they are. Instead of being a horizontal line or a vertical line, it's a slanted diagonal line that our graph approaches. So our definition, a slant asymptote is a line y equals mx plus b that is neither horizontal nor vertical, and as x approaches plus or minus infinity, the graph of f of x approaches this line. So these are the hardest ones to find, but luckily we already have all the skills that we need to find slant asymptotes. To find a slant asymptote, you're going to need to use either polynomial long division or synthetic division if the situation allows it. Now, the question is, do we always have to check for slant asymptotes? And the answer to that is no. Slant asymptotes only occur in a very particular situation. Our rational function, P over Q, has a slant asymptote if the degree of P of X is exactly 1 greater than the degree of Q of X. And then to find your slant asymptotes, long division. The quotient without the remainder is the slant asymptote. So you only have to check for a slant asymptote if the degree of the top is exactly 1 bigger than the degree of the bottom. Any other situation, you're not going to have a slant asymptote, so you should not bother trying to find it. Let's do an example where we have to find vertical asymptotes, horizontal asymptotes, and slant asymptotes, just to get all of our practice in. Find all of the asymptotes of g of x equals 2x squared minus 9 over x plus 1. I usually start with vertical asymptotes because they're the ones that people have been doing the longest, so it's ones we're most familiar with. Then I usually look for horizontal next and save slants for the end. So vertical asymptotes, remember, are where we divide by 0, but it's a situation where the numerator does not have that same factor. So I should look, can I factor this? Well, this 2x squared minus 9, if I try to factor it, I'm going to have to do some really complicated difference of squares involving a square root of 2. It doesn't factor very nicely. And it definitely does not have x plus 1 as a factor. So I know that my vertical asymptote is just where I divide by 0. X equals negative 1. Notice when I plug that negative 1 into the top, it's not 0 in the top. That's why I know that that's not a common factor. Horizontal asymptotes. Look at the degrees. The degree of the numerator is 2. Degree of the denominator is 1. Since the numerator has higher degree, I know that there are no horizontal asymptotes. And then last we have slant asymptote. Is the degree of the numerator exactly 1 bigger than the degree of the denominator? Yes. This means we have a slant asymptote. So to find the slant asymptote, I have to divide these two polynomials. I'm going to use synthetic division just because I'm dividing by something of the correct form for synthetic. So we have a negative 1 in the box, coefficients of 2, 0, negative 9. Bring down the 2, multiply and add, multiply and add. Now remember, this negative 7 was the remainder. But my slant asymptote is the quotient without the remainder. So I don't need that negative 7. I'm just going to have this y equals 2x and minus 2 is my slant asymptote. So you get it just by doing our synthetic division or long division. I personally would do synthetic division anytime that I'm dividing by x plus or minus some number. Otherwise, use long division. All right, so to finish up this video, we now get to put all of this together and graph some rational functions. So I'm going to give us the steps for how to graph rational functions, and we're going to do 2 examples graphing. Step 1, find the x and y intercepts. Remember, your y-intercept is what you get when you plug in x equals 0. Now your x-intercepts, you can find those by where the numerator equals 0, but the denominator is not 0. After you find your intercepts, find all of your asymptotes. That means vertical, horizontal, and slant. Once you've found your asymptotes, find points where your function crosses the horizontal asymptote or slant asymptote, if you can and if it does. So you should always check this. If you have a horizontal asymptote or a slant asymptote, check to see if your function crosses it at any particular point. Then plot at least one point in between all of the found points and asymptotes from steps 1 through 3. So steps 1 through 3, we found some intercepts, we found some asymptotes, and we potentially found some points on the asymptotes. Step 4 is to just find at least one point in between all of these other ones. Then step 5 is just sketch. So let's go ahead and do a couple examples of this so you get the idea. So we are going to graph g of x equals negative 5x over x squared minus 9. And I know I'm eventually going to have to find asymptotes, so we're going to have to do some factoring. So I'm just going to go ahead and factor this right away. If I factor the denominator, I get an x plus 3 and an x minus 3. So first step, find all of the x and y intercepts. Let's find the y-intercept first. To find the y-intercept, you plug in 0. This means I will have negative 5 times 0 on top, 0 plus 3, and 0 minus 3 on the bottom. That's 0 over negative 9, which is 0. So my y-intercept is the point 0, 0. My x-intercept is any point that makes the numerator 0, but doesn't make the denominator 0. Well, my numerator equals 0 when x is equal to 0. If I plug 0 into the denominator, I don't get 0. So that means the point x equals 0 and then y equals 0 is my x-intercept. So my x and y-intercepts are the same on this one. That happens a lot, but not all the time, so you should always check. Now, I need to find all of my asymptotes. So up in this upper corner, I'm going to keep track of all the things that we find. So far, I have a point at 0, 0. Let me rewrite my function. we had negative 5x over an x plus 3 and an x minus 3. So step 2 is finding all of our asymptotes. Start with the vertical ones. Your vertical asymptotes are where your denominator is 0, but the numerator is not. So I would get x equals 3 and x equals negative 3 as my vertical asymptotes. Those are the values that make me divide by 0, and I don't have common factors in the top. So I have vertical asymptotes of plus or minus 3. Horizontal asymptote. The degree of the numerator was 1. The degree of the denominator was 2. If you forgot that, remember, just redistribute at the bottom and you'll have an x squared. Since the degree of the denominator is larger, this means that y equals 0 is my horizontal asymptote. Do I have a slant asymptote? No, I don't have a slant asymptote because the degree of the numerator is not exactly 1 more than the degree of the denominator. So there is no slant asymptote. So now, step 3, I have to find any point where my function crosses my horizontal asymptote. My horizontal asymptote is 0. And if I try to solve where my function equals this asymptote, you multiply by the denominator, and you end up getting x equals 0. So I cross my horizontal asymptote at the point 0, 0. We already have that point in our list, so I don't need to write it down again. Step 4 is to find points in between all of my known points and asymptotes. So at this point, I would already start drawing my sketch and just put all that I know on the graph. So far, things that I know, I have a point at 0, 0. So there's my point at 0, 0. Then I have vertical asymptotes at plus or minus 3. So that means I'm going to put a dashed line at x equals positive 3 and x equals negative 3. Those are vertical asymptotes, so I can't touch those. My horizontal asymptote is my y equals 0 line. That's my x-axis. Kind of hard to put a dashed line on the x-axis because you already have your axis there, but I'm going to do it very lightly to remind myself. So now I need to find at least one point in each section that we have left. So I need to find a point over here before my asymptote, in between here, between my asymptote and my point, then between my point and my next asymptote, and something over on the right side of that last asymptote. So let's go on this side first. I need some point to the left of this vertical asymptote. So I'm just going to plug in x equals negative 4. That will get me a point. So let me do, if x equals negative 4, what is my function? That was g. Then g of negative 4 equals negative 5 times negative 4 over negative 4 plus 3 times negative 4 minus 3. So that means on the top I have 20. And on the bottom, I have a negative 1 times a negative 7. So that's positive 7. So g of negative 4 is 20 over 7, which is pretty close to 3. It's just under 3. So I'm going to have a point at negative 4 and just under positive 3. So somewhere right around here. So over on this side, so I match my asymptotes, my graph has to be curved like this, going up to infinity when it gets close to the vertical asymptote and flattening out to that horizontal asymptote. Okay, now let's find a value in between this vertical asymptote and my point. And I'm going to need to clear out some room so that we can do that. All right, so since I'm working right here right now, let me just write all the work over here. I need to find a value for some point in between here. So between -3 and 0. I'm going to use -1. G of -1 would be equal to -5 times -1 over -1 plus 3 times -1 minus 3. That's +5 over a +2 times a -4. So that is a -8. So I have a point at -1, -5/8. So let me try to find that. -5/8 is pretty close to -1/2. So here's -1, -5/8 is somewhere around here. So I know to match this vertical asymptote, I'm going down to -infinity and then coming up to hit that point. Now let's see what happens on this side. For that, I'm going to use +1, because that's a value between 0 and 3. If I use x equals +1, most of the work is the same. It's just I'm going to get a -5 over a -8, which is +5/8. So let me put a point at 1, +5/8, and connect matching my asymptotes. So it's going to go up to infinity for that asymptote. Now I just have one section left to check, something to the right of that last asymptote. So I have to pick something bigger than 3. I'll just use x equals 4. And since I'm going to be graphing somewhere over here, let me go back over here to do the work. If x is equal to 4, g of 4 will be -5 times 4 over 4 plus 3 times 4 minus 3. That's -20 over 7. So I would have at 4 a point down pretty close to -3, right about here. And again, matching my asymptotes, that means I have to be going down to infinity on that side. And I have to flatten out to my horizontal asymptote, so I get some graphs sort of like that. And if you have a graphing calculator, you can also type this function into your graphing calculator and you'll see this similar shaped graph. So there are a lot of steps to graphing rational functions, but at least we have a set order to follow to do it. Let's do one more example to finish this up. This last example I chose because it has a slant asymptote. We definitely want to practice graphing those. They're a little weird looking when you graph. So let's graph k of x equals 2x squared minus 7x plus 3 over x minus 2. And the first thing I'm going to do is factor this entire rational function. If you factor the top, you will get 2x minus 1 times x minus 3. We need to start by finding our intercepts. Your y-intercept is what you get when you plug in a 0 for your x. When you plug in 0 for x, you will get 3 over -2, or -3/2. So I have a y-intercept of 0, -3/2. Now my x-intercepts are where my numerator equals 0, but the denominator does not. I don't have common factors, so I can just set each piece of the numerator equal to 0 and solve. I get x equals 1 over 2 and x equals 3. So my x-intercepts are 1/2, 0, and 3, 0. So I have 2 x-intercepts, 1 y-intercept, and none of them match each other this time. That's okay. So like last time, I'm going to rewrite my function in its factored form over here. And I'm going to keep track of my points on the right side. I have 0, -3/2. I have 1/2, 0, and I have 3, 0. That's all I know of my graph so far. Now we need to find our asymptotes. So let's start with vertical asymptotes. Vertical asymptote is where the denominator is 0, but it's not a common factor with the numerator. So that's going to be when x equals 2. I divide by 0 there, and x minus 2 is not a common factor. So I know I have a vertical asymptote, x equals 2. Horizontal asymptote. The degree of the numerator this time is 2. Degree of the denominator was 1. The numerator has higher degrees, so this means there's no horizontal asymptote. But the degree of the numerator is exactly 1 bigger than the degree of the denominator. So I have a slant asymptote. I'm going to use synthetic division again. I have a 2 in the box. I have my coefficients, 2, -7, and 3 from the numerator. And now I do my synthetic division. Bring down the 2, multiply and add, multiply and add. And remember that your slant asymptote is the quotient part, not including the remainder. So I get y equals 2x minus 3 as my slant asymptote. Now I have to check, are there any points where I actually touch the slant asymptote? That's step 3. So to do that, you take your slant asymptote and set it equal to your function. And see if there's any places where this is true. Multiply by the denominator on both sides. And if I distribute everything on both sides, I get 2x squared minus 7x plus 6 equals 2x squared minus 7x plus 3. But if I try to solve this, I'm going to get 6 equals 3, which means there's no solution. And that's okay. That just means that our graph never touches the slant asymptote. And that happens sometimes. So, to graph this function now, start by putting all of the information that we have so far on the graph. So I'm going to put all of the points that I know on the graph and all of the asymptotes. And then I have to fill in points in between. So the points that I know, 1, 2, 3, 4, 1, 2, 3, 4. The points that I know are 1/2, 0. That's right here. I have 0, -3/2, and I have 3, 0. I have a vertical asymptote at x equals 2. And I have a slant asymptote at y equals 2x minus 3. To put the slant asymptote on there, you have to pretend you're graphing that straight line, but you graph it with a dashed line instead of a solid line. So 2x minus 3 would have a y-intercept of -3 and a slope of 2. So up 1 over 2, up 2 over 1. I did it right and said it wrong. Up 2 over 1, up 2 over 1, and I can connect those points with a dashed line. So I have this diagonal line that we're never going to touch. Now I just have to check for different points in each section. So I can already see a little bit here what's going on. I'm going to be flattening out to this diagonal on this side. And just to get one more point, let's plug in x equals 1 to get a little better shape right here. When x equals 1, my function k of x is equal to, in the factored form, I would have 2 times 1 minus 1 times 1 minus 3 over 1 minus 2. And when I simplify that, I get that k of 1 is equal to 2. So I have a point at 1, 2, and I want to connect this so that it curves up to the vertical asymptote and curves matching this diagonal line. Similarly, on this side, let me choose something. I'll do x equals 3 and also x equals, I guess, 2.5, just to get a little bit better of a shape. So if I do x equals 2.5, my function k is equal to 2 times 2.5 minus 1, so that's 5 minus 1, which is 4. 2.5 minus 3 is negative 0.5, and 2.5 minus 2 is 0.5. So I get 4 times a -1/2 is -2, divided by 1/2, I get -4. So I have a point at 2.5, -4, which would be down here-ish. Now, if I plug in x equals +4 to get one more point, my k of 4, if you plug it all in and simplify, you will get 7 over 2, which is the same thing as 3.5. So there's 3.5-ish, somewhere up there. And so if I connect this following my asymptotes, on this side I'm going down to my vertical asymptote. That's a little too curved. And I'm going to connect these, and it's flattening to that slant asymptote. And that's a really rough graph. There, that one's a little better. Kind of curves. It's a really weird, sort of like an X shape, but it doesn't touch in the middle. So personally, I think the ones with slant asymptotes are very ugly to graph, but you can also type it in your calculator and get a better idea of what it looks like. But that's the general procedure for graphing. And that's all I have for you today on rational functions. In our next video, we're going to be solving some polynomial inequalities rather than polynomial equations. So if you have any questions, drop them below. Or if you're a current student, you can ask in office hours or through email. And I'll see you guys next time.